We've talked about all the different rules that we need for something to be an ideal gas, right? How many assumptions do we have for something to be an ideal gas? 5. And there's lots of different things, right? They're in random motion. Okay, they have no attractive forces to each other. What are some other ones? Yeah, Braden, what do you think?
The temperature of the gas depends on the average kinetic energy.
Right, the amount of energy controls the temperature. What else? 2 more.
Continuous rapid motion.
Okay, continuous rapid motion. Anything else?
Elastic collision.
They have elastic collisions, which means they hit and they bounce off. Very good. Okay? Let's take a look at our gas laws. When we talk about gas laws, we're going to connect pressure, volume, and temperature of these gases. Okay, so we're going to talk about Boyles Law, Charles Law, Gay-Lussac's Law, and the combined gas law today. Have you heard any of those? Have you heard of any of those before?
Yes.
Yeah, a little bit, maybe. Okay. We're going to first talk about what we call STP units, and STP stands for standard temperature and pressure. Standard temperature and pressure. So those are kind of the baseline units. Okay, and I'm going to give you these STP units that you need to have in your notes. Okay, so it's a specific temperature and a specific pressure that we consider STP. Okay, and those specific units that go with temperature and pressure, temperature should always be measured in Kelvin. Kelvin. So Kelvin is just a capital K. When we want to convert from Celsius to Kelvin, so if we have something in degrees Celsius, we just add 273 to get it to Kelvin. Have you done that before?
Yes.
Okay, good. Okay, so we're going to convert from Celsius to Kelvin by adding 273. If you want to go back the other way, what should you do? You should subtract 273. If we need to go from Fahrenheit to Celsius, here is our formula for that. We don't do that near as often. Remember, everything in science is pretty much Celsius or Kelvin already. If we have to go from Fahrenheit to Celsius, we're going to use this formula here. From there, you could go from Celsius to Kelvin. Okay. Questions about those conversions? Okay, the most important one that we really need to remember is that Kelvin is Celsius plus 273. We're going to do that a lot. Okay. So now we're looking at pressure. So we looked at our standard temperature units. Now we're going to look at pressure, and we measure it in what's called atmospheres. Okay, have you heard the term atmospheric pressure before? Yeah, it's just the pressure that's around us all the time. It's what's in the atmosphere. So they've given it a unit called atmospheres. Okay? What pressure is essentially is how much force is acting in on us over a certain amount of area. Okay? So there can be pressure in this room, there's pressure within our bodies, how much force is working in a certain area. Okay? But pressure units have lots of different conversions. There's a lot of different ways to measure pressure. So I'm going to give you some conversion factors here that you're going to need to be able to convert from these specific units into atmospheres. Okay, so these are things that you might need to use a T-chart for. Okay, so STP, these are the conversions between these. Okay, so 1 atmosphere is equal to 101.325 kilopascals. Okay, kilopascals is another unit for pressure. So you can measure pressure in what we call kilopascals, but we like to keep it in atmospheres. So there's the conversion factor for that. Okay, and I'm going to give you several other conversion factors. Okay, there's tons of different ways to measure pressure. This is called millimeters of mercury. Millimeters of mercury is what you use to measure barometric pressure. Okay. Torr is another version of pressure, and PSI is our final version of pressure. What do we see PSI with? Do you ever see that? Yeah, in what? Tire pressure. Yeah, you see tire pressure, right? That's how your tire pressure is measured, and that's pounds per square inch. Okay, so you need to have each of these conversions, and we need to be able to convert pressure from one to another. That's what our homework is going to be over today, is converting these different pressure quantities. Okay, so these are the values for STP, and you absolutely have to know these in your notes and know what they are. Okay, so this is what we would use the most: 0 degrees Celsius and 1 atmosphere Kelvin, or 273 Kelvin. 1 atmosphere of pressure, or 273 Kelvin and 1 atmosphere of pressure, or 101.3 kilopascals. We really don't use that kilopascals hardly ever, okay? But our temperature is either 0 degrees Celsius or 273 Kelvin, which we know are the same thing. Okay, that's the same temperature. Sorry. Okay, 0 degrees Celsius and 273 are the same temperature, just like 1 atmospheric pressure and 101.325 kilopascals is the same pressure. Okay, these two are identical. These two are identical. They just have different units. Does that make sense to everybody? Yes or no? Yeah? Okay, good. So if I say I have 4 liters of a gas at STP, that's telling you I have 4 liters of a gas that's at 273 Kelvin and it has a pressure of 1 atmosphere. Okay, so we have to know those conditions. Questions here? All right. We're going to look at 3 specific gas laws today, maybe a 4th, but probably just stop after 3. And they are Charles, Boyles, and Guy-Lussac's law. Okay, you don't have to necessarily write these down because we're going to go into them individually, but I want to introduce you that we're going to have 3 of them specifically, and then we're going to be able to combine them all into one, cleverly named the combined gas law. Okay, so we're going to have 3 major ones today, and then we're going to combine them all into one. Okay, so let's look at Boyles Law first. Boyles Law first. Okay, this tells us that the pressure and the volume of a gas are what we call inversely related. That means if one goes up, the other goes down. Okay, if the pressure of a gas goes up, the volume typically goes down. When this works is when we have a constant temperature and constant mass, right? The number of particles in that gas are not increasing or decreasing. Just like the temperature is not increasing or decreasing. Okay, so we have to have constant mass and constant temperature in order for Boyle's law to work. We're going to relate pressure and volume in one equation. Here's our equation. Okay, P1 times V1 equals P2 times V2. And so here's what each of those variables mean. You don't necessarily have to write them down, but this is kind of just a way for you to see them. P always means pressure. V is volume. Just like P2 is pressure and V2 is volume. The 1 and the 2 tell us before and after. Okay, there's usually a change that takes place. Either it's, they've increased the pressure or increased the volume or something's been changed that we have a before and an after. Okay? Something that we should note is that our volume should always be measured in liters. Okay, liters. So if you're given it in milliliters, we're going to have to convert. So you need to know those prefixes again. Okay, all of that SI unit prefixes. So when we work these problems, we want to kind of make a list of what we have in our margins. Okay, kind of list what we have. So it tells us we have 1 liter of gas at STP, and it's compressed to 473 milliliters. So go ahead and take time and get this written down if you need to, and then we'll start together as a class. All right, so what does this 1 liter of gas tell us? Does that tell us our initial volume or our final volume? Initial, okay, and it's in liters, which is exactly what we want. So we have 1 liter. What about our final volume here? It's been compressed to 473 milliliters. How do we convert that to liters? Yeah, we divide by 1,000 or we move that decimal place 3 places to the left. So that would give us 1, 2, 3, which gives us 0.473 liters. We have to convert from milliliters to liters, otherwise this equation won't work. Our pressure will come out funny. Okay, we know that our first, at the beginning it's at STP. What's that mean the pressure is? 1 atmosphere, good. Okay, 1 atmosphere. And what about our final pressure? That's what we're solving for. Okay? So let's go ahead and plug that into some equations here. P1 times V1 equals P2 times V2. Okay, so 1 times 1 equals P2 times 0.473. All right, and how do I get P2 by itself? What do I need to do algebraically to get that by itself? Yeah, we divide 0.473 on both sides. And what does the pressure come out to be? What'd you get, Jake?
2.9.
2.1. And what was your units? Good. Atmosphere. Okay, 2.1 atmosphere. So does this agree with the relationship we said pressure and volume have? What happened to the volume? Did it go up or down?
Down.
It went down. And did the pressure go up or down? Up, right. So for Boyles Law, they're inversely related. If one goes down, the other goes up. Okay, if one goes up, the other goes down. That's how it works for Boyles Law. Okay? Okay, you don't have to write the whole problem down word for word. Just kind of summarize it a little bit. But if I have 0.5 or 5.6 liters at a pressure of 1.5 atmospheres and I compress it till it has 4.8 liters, what will the final pressure be? Okay, so our pressure came out at 1.75 atmospheres. Very good. Any questions? Okay, now we're going to take it up one little notch with our next problem. One point what?
03.
Okay, 1.03 atmospheres. That should make sense since our value started out at just over that 1 atmosphere mark. Okay, so we have 1.03 atmospheres. Our final volume was,
0.424.
good, 0.424 liters. And we're solving for our final pressure. Okay, so we're setting up our problem the same, except we had to do some conversions here. Uh-huh. Yeah, very good. Okay, Danny asked the question that we added 0.24 liters. Good. So that means what should we do? I'm sorry, I didn't catch that. We need to add that to our initial volume. Very good. Thank you for bringing that up. Okay, so our final volume is not just 0.424. It says we're adding volume to that. So that means we need to add it to our initial. Okay, very good. Which gives us what value as our final volume now, Danny? Thank you. 1.251.9. Okay. Very good. Okay, so now our equation should look something like this. 1.03. Uh-huh.
Okay, when I divided that in my calculator, I had gotten 12.
P2, which is what we're solving for, times V2, 1.259. And what did we get for our final pressure? Abby, what'd you get? 6.8. Sorry, what? 6.8? 3. Good. ATM. Good. Okay, so did our volume go up or down? Our volume went up, so what happened to our pressure? It went down. Very good. Okay. Okay, Charles' law tells us the volume and the temperature of the gas are directly related. So on the last problem, they were indirectly or inversely related. Now these two are directly related. Okay, which means if one goes up, so does the other. If one goes down, so does the other. So here's kind of what our graph looks like. You see as the volume increases, so does the temperature. Same way, if the volume would decrease, so would the temperature. Okay, going on this line right here. Decreases it, both of them decrease. If it increases, both of them increase. Okay, so we're going to compare our two conditions, right, our before and our after with this equation here. V1 over T1 equals V2 over T2. This is Charles' law, so this could go on your equation sheet as well. All right, so we have Boyles' law, which is pressure and volume. Now we have Charles' law, which is volume and temperature. Okay, so let's try one here. 63 liters of helium in a balloon that's 28 degrees Celsius. I increase the temperature to 47 degrees Celsius. What will the final volume be? Okay, so write down what you need to, and then we'll get started with it. So I have my initial volume at 67 liters. My initial temperature is 28 degrees Celsius, which converts to what in Kelvin?
301.
301, good. 301 Kelvin. My final volume is what we are solving for. And my final temperature, 320. Do we agree with all those variables? All right, good. So we're going to do V1 over T1 equals V2 over T2.
Where the heck did you get the...
Okay, do we all agree there? 71.23. How do we solve problems like this? Cross multiply and divide. Cross multiply and divide. Okay. So we would have had 67 over 301 equals V2 over 320, which means we're going to multiply here, then divide. 320 times 67 divided by 301 gives us 71.23 liters. Yeah? Are we all getting it to come out in your calculator? Okay, I want to make sure everybody's being able to plug that in. All right, so knowing that our volume decreases, what should happen to our temperature? Decrease. It should decrease, okay? So when we set up our equation and we solve for T2, okay, Braden, what'd you get?
For T2.
Uh-huh.
21.1 Celsius or 294 Kelvin.
294 Kelvin or what?
21.1 Celsius.
Okay. Does everyone agree there? That's not, I thought I had a little higher than that.
No,
Okay. I think I had a little higher than that. Jenna, what'd you have?
341.96.
Okay, is everybody on the same page there? Okay. And we don't have to convert it back to Celsius. You can if you want, but I'm okay with just leaving it in Kelvin there. Uh-huh.
This is not matter, it's just like one.
Make sure to convert that Celsius to Kelvin by adding 273. All right, Andy, what'd you have for T2?
518.26.
Good. And what's our units?
Kelvin.
Good. All right, that's what I had too. Does everyone agree with that? 518.26? Okay, and I'm really okay with you rounding that temperature to a whole number, especially since it's so high. Okay. Any other questions there? Those are our two main gas laws. We're going to look at the final one here called Boyles Law, and that's where we relate the last two things, pressure and temperature. Okay, and this is kind of the least used of our gas laws. I don't really know why, but no one really uses this Boyles Law very much. But this is where we relate pressure and temperature. Can anyone take a guess about what our equation might look like based on what we know already? Anybody have a guess? Or not really? Perfect. Okay, it's going to be P1 over T1 equals P2 over T2. And the way we know that, good job, Jenna, the way that she knows that is because we're taking pressure times volume equals pressure times volume. So it should look just like our volume and temperature relationship. When it tells us these two are directly related, that means as pressure increases, so does temperature. Okay, or as pressure decreases, so does temperature. If one goes up, so does the other. If one goes down, so does the other. just try one quick Gay-Lussac law problem here on the bottom, real quick. We won't work with that gas law quite as much. All right, Carolyn, what do you have for P2 here? Do you have a final answer yet? Okay, okay. Andy, what'd you have? 1.03 ATM. Grant, do you agree? Yes. Yeah? Everyone else agree? Good. Okay, our temperature increased, so our pressure should increase. Did our temperature increase a great amount?
No.
Not really. So that explains why our pressure doesn't increase a great amount. Okay?